Drive northeast out of Los Angeles for about 140 miles and the country empties out fast. Barstow, then Joshua Trees, a rail crossing, a diner with a hand-painted sign, then the gate for Fort Irwin, where the army trains tank crews on ground that looks close enough to a desert war. Deep inside that reservation, in a valley the army loaned to NASA in the 1950s, there is a steel dish 230 feet across. It weighs close to 3,000 tons, and it rides on a film of oil so it can turn without shaking. Right now it is pointed at a spot in the northern sky where there is nothing to look at. It is listening to a radio transmitter that runs on 23 watts. Your refrigerator bulb burns 40. A bike taillight burns 2. That signal has to cross more than 15 billion miles of vacuum before it gets here. And by the time it arrives, the power landing on that dish is about 1/billionth of a watt. There is a line the engineers at the Jet Propulsion Laboratory use when somebody asks them to put that in perspective. All the energy ever collected from every deep space mission NASA has ever flown, added up together, comes to less than the energy of a single snowflake hitting the ground. They catch it anyway, every day, 50 years running, and the machine sending it was finished before Star Wars opened in theaters. The dish has a number, Deep Space Station 14, and a name nobody at the site bothers with. Everyone calls it the Mars Antenna. It went into service in 1966, and it picked up the name after it tracked Mariner 4 through the long months following that spacecraft's flyby of Mars, including the stretch when the probe passed behind the sun and everybody expected to lose it. The name stuck the way names stick at government facilities. 60 years later, the sign still says Mars. There are 3 dishes in the world in this class. 1 at Goldstone, 1 outside Madrid, 1 outside Canberra, spaced roughly a third of the way around the planet from each other, so that as the Earth turns, one of them always has a view into deep space. Together they are the Deep Space Network, and they are the only ears our species owns that are good enough for this particular job. Here is what makes the job hard. In physical terms, a radio transmitter does not throw a beam. It throws a cone. Voyager 1 has a high-gain antenna 12 feet across that narrows that cone as much as physics allows. And it is still a cone. After 15 billion miles of spreading, the cone is wider than the Earth, wider than the Moon's orbit. The dish in the Mojave catches a slice of it about the width of a football field, and that slice contains almost nothing. To hear it, the receiver has to be quieter than the signal itself. That is the whole engineering problem in one sentence. Electronics generate noise just from being warm, and at room temperature, the hiss inside an ordinary radio receiver would drown out anything coming in from Voyager thousands of times over. So the front-end amplifier at Goldstone sits in a bath of liquid helium, held a few degrees above absolute zero, until the metal stops whispering to itself, when even that is not enough. They gang antennas together. In 2024, when Voyager 1 was in serious trouble and the team needed every fraction of a decibel they could get, engineers in Spain arrayed 6 separate dishes at the Madrid complex and combined their signals into one. 6 dishes. To hear 23 watts. Now watch a conversation happen. It starts in a building at JPL in Pasadena, up against the San Gabriel foothills, where the Voyager team works out of an office you would walk past without noticing. There is no wall of screens. There are desks, a whiteboard, a coffee maker that has outlasted several project managers, and a small number of people. Fly both Voyagers and you could seat the entire flight team at 2 conference tables with chairs left over. Somebody builds a command sequence. Somebody else checks it. Then a third person checks it. Because there is no undo out there, and everybody in that room knows it. The sequence goes over a line to Goldstone, into the transmitter, up the feed cone, off the dish, and into the sky. Note the time. Everything after this is waiting. The command leaves the desert at the speed of light. which sounds instantaneous until you hang a distance on it. 1 1/3 seconds to the moon, 8 minutes to the sun, about 43 minutes to Jupiter's orbit, roughly 23 hours to Voyager 1. If the spacecraft answers, the answer takes another 23 hours to come home. That is the working condition on this mission. 46 hours between a question and an answer. You send an instruction to a machine. You go home. You sleep. You come back and work a full day. You go home and sleep again. And then you find out whether what you did helped or whether you just killed the farthest object human beings have ever made. Suzanne Dodd has been managing this mission since 2010. She worked on Voyager as a young engineer in the 1980s building command sequences, left for other missions, and came back 20 years later to run it. She has described the tempo of the job about as plainly as it can be described. Every decision takes 2 days to hear back on, and if the news is bad, it is already 2 days old. There is one more number worth having before we go anywhere, because it is about to change the shape of that weight. A light day is exactly what it sounds like. The distance light covers in 24 hours, which works out to around 16 billion miles. For the entire history of the human species, nothing we built had ever been that far from home. And for most of that history, the sentence would not have passed. Voyager 1 crosses it this November, the 18th, by NASA's reckoning. After that date, every exchange with this spacecraft costs more than 2 full days round trip, and the number only climbs. It never comes back down, so the command is out. It cleared the moon's orbit a second and a third after leaving the dish, and it will be past Mars before the shift at Goldstone ends. It is headed for a spacecraft that weighs about 1,600 pounds, carries a gold-plated copper phonograph record bolted to its side, and was drawn up on drafting tables by people working slide rules. Most of those people are retired now. A lot of them are dead. The spacecraft is still working. It launched carrying 11 scientific instruments. It has been shedding them for decades, one at a time, deliberately, on a schedule somebody wrote out years in advance. It has 2 left. On the 14th of November, 2023, the engineering telemetry from Voyager 1 turned to garbage. The carrier signal was still there. That mattered more than anything else on the screen that day, because a steady carrier meant the transmitter was on, the antenna was aimed correctly, and the spacecraft was alive. Commands went up, and Voyager acted on them. It heard everything. It just could not say anything. Every spacecraft sends home 2 kinds of data. There is science data, which is the point of the mission, and there is engineering data, which is the spacecraft describing itself. Temperatures, voltages, which systems are powered, whether attitude control is holding. Engineering data is the only way the ground knows anything at all about the condition of a machine no human being has laid eyes on since the summer of 1977. What came back that November was a repeating block of 1s and 0s, the same pattern, over and over, carrying nothing. Instrument readings gone, temperatures gone, status flags gone. Ideal tone. Picture the room in Pasadena that week. You cannot power cycle it. There is no reset button, and even if there were, sending a blind restart to a computer whose state you do not understand is how you turn a working spacecraft into a monument. You cannot swap the part. The part is 15 billion miles away, sealed inside a machine that was closed up in a clean room in Southern California during the Carter administration. You cannot test the fix somewhere safe first. There is no flight spare sitting in a warehouse running the same hardware in the same configuration with the same 46 years of patches loaded into it. Voyager 2 is out there, but it is a different spacecraft now, with its own history of failures and workarounds. Whatever you try it on the real thing, and you cannot iterate. Every attempt costs about 46 hours. Send a command. Wait almost 2 full days. Look at what comes back. Think about it. Send another one. For 5 months. That was the job. The team that took it on is the group from the last chapter. small enough for 2 conference tables. Some of them have been on Voyager for 30 years. Some were not born when it launched. And when the problem got deep enough, they started making phone calls to people who had retired, in some cases decades earlier, because the knowledge they needed was not written down anywhere useful. Hold that image, because it is where this whole story is going, and we are taking the long way to get there. There is a reason that repair took 5 months, and a reason it worked at all, and neither reason lives in 2023. They live in a set of decisions made at JPL in the early 1970s, in a design philosophy that went out of fashion 40 years ago, and in the specific route this spacecraft took through the solar system, which was chosen once and could never be taken back. We have a way to walk that route. The command we sent in the last chapter is still going. It cleared the atmosphere in a fraction of a second and passed the moon's orbit 1 1/3 seconds later. It is already farther from Earth than any human being has ever travelled. It has 23 hours to run. In the first hour of that flight, this signal will cross every mile of space that Voyager 1 spent the first 3 years of its life exploring. All of it. Jupiter, Saturn, the moons, the photographs that ended up on posters and textbook covers and the walls of every planetarium in America. The whole famous part, in the first hour, which leaves 22 more. That ratio is the honest answer to what this spacecraft is. And it is why the story cannot be told as a straight line from launch to now. So we are going to follow the signal instead. Every time it crosses a region, we stop and find out what happened there. It reaches the asteroid belt in about 20 minutes. And before it gets to Jupiter, we have to settle something. Because Voyager 1 was never supposed to reach Jupiter. Not this spacecraft. And not on this trajectory. The mission it was built for got cancelled before the hardware was finished. What flew in 1977 was the thing that survived the budget cuts. Built by a group of engineers who had just watched the best idea of their careers get taken away from them. Stay with this one. The part most people have never heard is not the launch, and it is not the pictures. It is what those engineers did in the 2 years after the cancellation. And you can still see the evidence of it in the spacecraft's power readings tonight. The warranty was 5 years. That is not a turn of phrase. When a spacecraft gets built at a NASA center, an engineer writes down a design lifetime, and then every component on the vehicle gets qualified against it. Radiation tolerance, thermal cycling, bearing wear, propellant margin. Somebody signs the paper. The number for Voyager was 5 years, and the reasoning was simple. 5 years covered the cruise to Jupiter, the cruise from Jupiter to Saturn, and both encounters. After Saturn, the spacecraft had no assigned work, because in the documents that got the program funded, there was nothing after Saturn. Think about what else came with a warranty in 1977. A new car that year carried something like 12 months or 12,000 miles. Those cars are gone. Not most of them. Effectively, all of them. Except the ones that live under canvas in garages and come out for shows on Saturday mornings. There are no 1977 Chevrolets doing daily commutes on Interstate 10. The Apple II went on sale that June. The Commodore PET showed up the same year. A pocket calculator was still a purchase you thought about for a week. Home video meant a Betamax deck that cost more than most families cleared in a month. The Walkman was 2 years from existing. Voyager 1 is contemporary with every one of those things. Same decade. Same electronics industry. In some cases, the same suppliers and the same fabrication lines. All of those products went obsolete, got discontinued, ended up in landfills, and were forgotten inside of 10 years. The spacecraft has been running continuously ever since. No maintenance. No physical repair of any kind. Hard vacuum. 49 years. There is a temptation here to turn this into a story about how they built things right back then. And I want to hold that off for a minute. Because the real answer is more specific than nostalgia, and it explains more. Part of it is the environment. Space is brutal in ways everybody knows about. And it is also remarkably stable. No humidity. No oxygen. No dust working into bearings. No road salt on the connectors. No vibration except what the spacecraft makes itself. A machine that survives launch and then floats in vacuum at a steady temperature is not aging the way anything on Earth ages. Part of it is disuse. Voyager 1 has almost no moving parts left in service. The tape recorder is off. The scan platform stopped swiveling decades ago. What remains is mostly solid state. And solid state electronics, with nothing mechanical attached, will run a very long time if you keep them powered and keep them warm. But most of it comes down to choices made by a specific group of people in Pasadena. In rooms with drafting tables and slide rules, working at a moment when they had every reason to believe this was the last shot anybody was going to get. They built in redundancy the requirements did not ask for. 2 of nearly everything. On separate power buses. They built in power margin the mission did not need. They loaded more hydrazine than a 4-year flight would ever burn. And they built the flight computers so the software could be completely rewritten from the ground after launch. That last one was not standard practice in 1975, and it turned out to be the single most valuable decision anybody made on the entire program. None of that was free. Every bit of it cost mass. And mass on a launch vehicle is the most expensive commodity in the business. Engineers fight over ounces. So the question worth asking is why a team would spend that kind of margin on a 5-year mission. They did not think they were building a 5-year mission. They thought they were building something else. And they had been told, in writing, by the agency that signed their paychecks, that they were not allowed to. In the summer of 1965, a graduate student named Gary Flandreau took a summer job at the Jet Propulsion Laboratory. He was 21, working toward his doctorate at Caltech, and the assignment he got was the kind you hand a summer hire. Go look at ways to send a probe to the outer planets. See if any of them are worth pursuing. He worked it by hand, plotted the positions of Jupiter, Saturn, Uranus, and Neptune against time on graph paper, looking for anything useful in the geometry. What he found sat in the late 1970s. The 4 planets were going to line up, not in a row, which is not what the phrase means and not what matters. What mattered was that for a window of a few years, the 4 would sit in positions where one spacecraft could swing past each in sequence, using the gravity of each planet to fling itself toward the next. The window opens about once every 175 years. The last time it came around, Thomas Jefferson was in office, and nobody on Earth knew Neptune existed. Here is the physics. In the simplest, honest form, a spacecraft falls toward a planet and picks up speed. Then it swings around and climbs back out. And it loses exactly what it gained. Relative to the planet, it leaves at the same speed it arrived. Nothing gained. The trick is that the planet is moving. Come in behind a planet as it travels along its orbit, and the planet's gravity drags the spacecraft along in its direction of travel. When the spacecraft leaves, it is still moving at the same speed relative to the planet. But the planet has hauled the entire encounter downstream while it was happening. Relative to the Sun, which is the only frame that gets you anywhere, the spacecraft comes out faster. The energy is real, and it has to come from somewhere. It comes out of the planet's orbital motion. Jupiter is slowed by the encounter, by something on the order of a foot per trillion years. Jupiter can afford it, without gravity assists. A mission to Neptune with the rockets of that era would have taken about 30 years and a launch vehicle nobody was going to build. With them, 12. JPL called it the Grand Tour. 4 spacecraft, nuclear power sources, a new self-repairing computer architecture called STAR that was supposed to survive a decade in flight. Around $1 billion in 1970 money. In December of 1971, NASA cancelled it. The reasons were the ordinary reasons things die in Washington. The agency was coming down off Apollo with a shrinking budget and a mandate to build the space shuttle. Viking was eating money on its way to Mars. A $1 billion program to visit planets most taxpayers could not place on a chart did not survive the markup. What survived was a smaller thing with a name only an engineer could love. Mariner, Jupiter, Saturn, 1977. 2 spacecraft, 2 planets, 4-year mission, roughly a quarter of the money. The people who had spent 6 years on the Grand Tour were now assigned to build the consolation prize. So look at what they actually built, and then decide for yourself what they had in mind. The 3 radioisotope generators were sized to deliver about 470 watts at launch. A Saturn flyby needed a fraction of that. The margin was justified in the paperwork as insurance, which is easy to justify, because nobody in aerospace has ever lost an argument by asking for more power. The electronics were hardened for Jupiter's radiation belts, with a large factor stacked on top of the worst-case estimate. Easy to justify. Nobody knew how bad those belts really were, and the pessimistic number was frightening enough that no reviewer was going to push back. The propellant tank went out full. About 100 kilograms of hydrazine, far more than a 4-year mission would consume holding its antenna steady. Easy to justify. Attitude control failures kill spacecraft. The tank was already there, and topping it off costs almost nothing in the review. Each of those decisions defends itself on its own. Put them side by side and they describe a vehicle built to run for decades. And then there is the computer memory. The flight software on Voyager can be completely rewritten by command from the ground. Every word of it. The stated justification was protection against a software bug discovered after launch, which is a real risk and a reasonable thing to design for. It also means the spacecraft can be handed entirely new jobs, indefinitely, by engineers who had not been hired yet, working on missions nobody had thought of. That capability is the reason there is a story to tell in 2024. Without it, the memory failure we opened this video with would have ended the mission in a week. The name changed in the spring. In March of 1977, 5 months before launch, NASA held a naming contest and settled on Voyager. Mariner, Jupiter, Saturn did not sound like something that went anywhere else. And by then, a number of people at JPL were quietly hoping it might. So the team had 2 spacecraft with a stated mission of 4 years and hardware that could plausibly run for 30. What they could not do was put that in a document, because there was no money for a longer mission and asking for it would have reopened the whole program to review, which set the terms for everything that came after 1980. This spacecraft would have to earn its funding 1 budget cycle at a time, forever, by producing results nobody had planned for. None of it mattered if the antenna drifted. Voyager 1's high-gain dish has to stay pointed at Earth within about 1/4 of a degree. That is roughly a dime held at arm's length. Miss by more than that, and a signal already arriving at 1/1000,000,000th of a watt drops below what the network can pull out of the noise. And the spacecraft is gone. Not damaged. Unreachable. Still flying. Still transmitting. With nobody able to hear it, and no way to tell it to turn around. Holding that pointing is the job of 16 thruster nozzles. Each one is smaller than your fist. They have now fired several 100,000 times, and every single firing leaves something behind inside the plumbing. Before any of that could happen, somebody had to build the thing. 2 of them. Actually, in a high bay in Pasadena, by hand, with a launch window that would not wait. The Jet Propulsion Laboratory sits on 170 acres of the Arroyo Seco, wedged up against the San Gabriel Mountains where Pasadena runs out of flat ground. It started in the 1930s as a group of Caltech students setting off rocket motors in a dry riverbed, which went about as well as it sounds and got them the nickname the Suicide Squad. By the 1970s, it was a NASA field center with a few thousand employees, its own culture, and a chip on its shoulder about Houston. Building 179 holds the high bay. It is a clean room, which in practice means a very large white space with filtered air and a floor you could eat off, kept at positive pressure so dust blows out instead of in. Anyone who goes in wears a bunny suit, hood, boaties, gloves, no cosmetics, no loose paper, no cardboard. 2 spacecraft went together in there between 1975 and 1977. They were assembled by hand. That deserves a beat. Because it runs against how people picture NASA. There was no automated line. Technicians stood at the vehicle with hand tools, torque wrench, and paper travelers, mounting components one at a time and signing off each step. The wiring harness on a Voyager runs about 10 kilometers of copper, and every conductor in it was routed, dressed, tied down, and continuity checked by a person. Some of those technicians had been building spacecraft at JPL since the Ranger program in the early 60s, and had watched 6 Rangers fail in a row before the 7th finally sent back pictures of the moon. The engineering staff skewed young. This is one of the things people forget about the American space program in that era. The average engineer in the room was in his late 20s or early 30s. They had come up through Mariner, the workhorse planetary program, and a lot of them had joined NASA out of college during Apollo. When the agency was hiring anyone who could pass a physics exam, the rule of thumb inside JPL was that Voyager was staffed by people young enough to still be there when it arrived. That turned out to matter more than anyone intended. Here is the atmosphere in that building in 1975, which is not the atmosphere of a triumphant program. The Grand Tour had been dead for 4 years. Every person in the high bay knew they were building the cut-down version. There was open frustration about it, and there was also a running understanding, never written into any document, that the hardware they were putting together was better than the mission it had been assigned. John Cassani ran the project. He had been at JPL since the 50s, had worked Ranger and Mariner, and he had a reputation for 2 things. He protected his people, and he did not lose arguments about margin. Cassani is the one who pushed the naming contest that turned Mariner, Jupiter, Saturn into Voyager, and when reporters asked him later about the extended mission, his framing was consistent. They designed for the mission they had and built for the mission they wanted. Charles Colhays did the trajectory design. Colhays's job was to work out the exact path each spacecraft would fly, and the number of possible trajectories through the Jupiter and Saturn systems ran into the tens of thousands, once you accounted for every combination of moon flybys and arrival geometry. He and his team narrowed it down with computer runs that took overnight to complete an hand analysis that took weeks. The final Voyager 1 trajectory was selected out of about 10,000 candidates. Ed Stone was the project scientist. He came on in 1972, at 36, out of Caltech, where he had been building cosmic ray instruments. His job was to referee, which meant standing between 11 science teams who all wanted the same limited resources: pointing time, data rate, power. He held that job until 2022, 50 years, 1 spacecraft. There is a detail about how they worked that says more about the era than any of the hardware does. Every design decision, every anomaly, every trade study got written up, typed on IBM Selectrics, mimeographed, distributed, and filed. Schematics were drawn on vellum with pencil and India ink and stored in flat files. Interoffice memoranda explaining why a particular capacitor was chosen over another went into binders, and the binders went into cabinets. Nobody was doing that for posterity. They were doing it because that was the process, and because in a program where the engineer who designed a subsystem might be assigned somewhere else by the time it flew, the paper was how the knowledge moved. Those cabinets are still at JPL. In 2024, they saved the mission. Now the hardware itself. And I want to do this the way you would if somebody walked you around the vehicle before it got wrapped. The body is a 10-sided aluminum ring, about 6 feet across, hollow, with electronics bays built into each face. The whole vehicle weighs about 1,600 pounds fueled, and about 1,820 at launch with the propulsion module attached. Sitting on top is the high-gain antenna, 12 feet of graphite epoxy dish, and it dominates the spacecraft visually the way a satellite dish dominates a roof. Everything else looks bolted on around it. 3 booms come off the body. One carries the science instruments on a scan platform that can swivel on 2 axes. One carries the magnetometers, 43 feet out. That far because the spacecraft's own electronics generate magnetic fields that would swamp the readings. And one carries the power supply, also held away from the body. because it puts out radiation the instruments would otherwise pick up. 2 antennas for the plasma wave instrument extend in a V, 33 feet each, and bolted to the outside of the ring, near the base of the antenna structure, is a 12-inch aluminum cover with a phonograph record inside it. The whole assembly stands about the height of a 2-story building once the booms are deployed, and it will never be inside an atmosphere again. In the summer of 1977, the spacecraft went to Florida in the belly of a cargo aircraft, and technicians at Kennedy Space Center ran the final checks. One of the last items on the list was the record. There is a photograph from the summer of 1977 of a technician in a white smock and cap, leaning over the side of Voyager 1 at Kennedy Space Center, torquing a bolt. What he is attaching is a gold-plated copper disc, 12 inches across, sealed inside an aluminum cover. Almost everyone knows what it is. Very few people know what problems it had to solve. Start with the hardest one, because it drove everything else. You are putting information on an object that will be out there for a very long time. No power, no reader, no drive. Anything with a chip in it dies the moment the generators quit. Anything magnetic gets scrubbed by cosmic radiation over long enough spans. Anything printed fades. And anything organic is simply gone. So the information has to live as physical shape. Grooves cut into metal, a deformation you could read with a needle, or a microscope, or a laser, or a fingernail. Because a shape does not need a format. That ruled out tape. It ruled out anything electronic. What was left was a technology from 1877, a phonograph record, copper for the substrate, gold plating over it, partly for corrosion resistance and partly because gold is chemically lazy and will still be gold in 100 million years. A cartridge and a stylus mounted right beside it, so whoever finds it does not have to build a player. And etched into the aluminum cover, a set of diagrams showing the rotation speed, the direction of play, and how the signal converts back into a picture. That last item was the second problem. They wanted images. A record carries audio, which is a single value changing over time. A photograph is a 2-dimensional grid. The fix was the same trick that makes a fax machine work. Scan the picture line by line. Turn the brightness along each line into a varying tone. Lay the lines end to end, and the rectangle becomes a stream. Play it back and it screeches. Feed it into anything that can rebuild the raster, and the picture comes back. They encoded 115 images that way. A diagram of DNA, human anatomy, a woman in a supermarket, a man eating, traffic in India, the Golden Gate Bridge, a page from a book. So somebody could see what our writing looks like sitting still. The third problem is the one I keep coming back to. How do you say when the record was made? To someone who does not share a calendar. A year 0, or the idea of a year. Uranium-238 has a half-life of about 4.5 billion years. Electroplate a small patch of it onto the cover, and it starts counting down the moment the spacecraft is sealed. Measure how much has decayed into its daughter products. Compare the ratio against the known half-life, and you get elapsed time. It works for anyone in the universe who has done basic nuclear physics, which is anyone who could have found the spacecraft in the first place. A clock with no battery and no gears, running accurately since 1977, and it will keep running long after the metal it sits on has been pitted by dust. Now the part that keeps this from turning into a shrine. The committee had about 6 weeks. Carl Sagan chaired it. Andrew Yan was the creative director. Timothy Ferris produced. Frank Drake handled the technical side. They were assembling a document meant to outlast the continents on a schedule most people would consider tight for a wedding. They wanted a Beatles song. The band was reportedly willing. The rights sat with the record company, and the clearance did not come through in time. Here Comes the Sun is not on that record because of a licensing department in 1977. They wanted the human body illustrated, and one of the images showed a nude man and woman. NASA headquarters was still bruised from the reaction to the Pioneer plaques a few years earlier. When congressmen and newspaper columnists had objected to sending nudity into space on the taxpayer's dime, the photograph got pulled. What flew was a silhouette diagram. They recorded greetings in 55 languages. They put on whale song, thunder, footsteps, a heartbeat, our kiss, a Saturn V launch, and Chuck Berry playing Johnny B. Good. Bach and Beethoven and Louis Armstrong and Blind Willie Johnson. A Navajo night chant. Yevanissa Gamelan. A Bulgarian shepherdess singing alone. And in the last days before the deadline, Anne Druyan went to a lab at Cornell and had her brainwaves and heartbeat recorded for an hour while she deliberately thought about specific things. That hour is compressed into about a minute of sound on the disc, and it will outlast the species that made it. Sagan was clear about the odds, and he said so at the time. The chance of anything ever finding it is essentially zero. He described the record as a message to ourselves, a statement about what we thought was worth sending. Frank Drake put it more bluntly in later interviews. The real audience was on Earth. The record went into its cover. The cover went onto the spacecraft. A technician torqued the bolts to spec, signed the Traveller, and moved on to the next work order. Then the shroud came down over Voyager 1, and no human being has touched it since. Voyager 2 launched on the 20th of August, 1977. Voyager 1 launched on the 5th of September, 16 days later. That is not a typo, and nobody made a mistake. The numbers were assigned by which spacecraft would arrive first, and Voyager 1 went up on a shorter, faster trajectory that would let it overtake its twin somewhere in the asteroid belt and reach Jupiter 4 months ahead, which is what happened. Voyager 1 passed Voyager 2 in December of 1977, about 3.5 months out from Earth, and never gave up the lead back. Almost nobody tells the next part. Voyager 1 came very close to not getting out of the atmosphere. The launch vehicle was a Titan IIIe with a Centaur upper stage. The Titan does the heavy lifting off the pad. The Centaur takes over high up and does the precision work of putting the payload on an interplanetary trajectory, and it burns liquid hydrogen, which is cold, difficult, and unforgiving. About 4 minutes into the flight, the Titan's first stage shut down early. A leak in the hydraulic system had bled off pressure, and the stage quit before it delivered its planned performance. The Centaur's guidance computer noticed the shortfall and did exactly what it had been built to do. It kept burning to make up the difference. It ran through its first ignition, coasted, and burned again, compensating the whole way, spending propellant it had not budgeted for. It made orbit. It made the trajectory. When the engines finally cut off, the Centaur had about 3.5 seconds of usable propellant left in the tanks. 3.5 seconds. On a launch that lasted the better part of an hour. If the Titan's leak had been slightly worse, or had started a little earlier, the farthest object humanity has ever built would be sitting on the floor of the Atlantic, off the coast of Florida. And the only people who would remember the program would be a failure review board. Nobody at Kennedy knew how close it had been until the telemetry got analysed afterward. On the day, it looked like a normal launch. Then, 48 hours later, the second problem showed up. Voyager 1 carries a scan platform, a movable mount on the end of a boom, holding the cameras and several other instruments. It swivels on 2 axes so the spacecraft can aim its cameras without turning the whole vehicle and losing antenna pointing. It is the most important moving part on the vehicle. During post-launch checkout, it jammed. The team ran it through its motions and one axis would not go where commanded. The cameras were stuck. Every image the mission was designed to collect depended on that joint. And the spacecraft was already 2 days gone and accelerating away at a speed nothing on Earth could match. They worked it for days, exercised the mechanism, ran it back and forth, watched what the resistance in the telemetry was doing between attempts. Eventually it freed up. The diagnosis was debris in the mechanism, most likely a fragment of insulation shaken loose during launch, that worked its way out under repeated motion. That was the first time the Voyager team had to fix something they could not reach. And every technique they used that week is the same one they would be using 46 years later on a dead memory chip. Exercise the hardware. Watch what the numbers do. Form a theory. Test it. Wait. The waiting was shorter in 1977. That was the only real difference. The spacecraft was now on its way to Jupiter. Arriving in March of 1979, our command is going to cross that same distance in about 35 minutes. The pictures did not arrive the way pictures arrive now. Voyager 1 took an image with a Vidicon tube, which is television camera technology, not a digital sensor. The tube scanned its target, turned brightness into voltage line by line, and handed 800 lines of 8-bit values to the flight data system, 5.12 million bits per photograph. At Jupiter, running at its best rate, the spacecraft could push about 115,000 bits per second down to Earth, 45 seconds a picture at best, and often much slower. So through the winter and spring of 1979, people in the control rooms at JPL watched Jupiter come in the way a Polaroid develops. Top of the frame first, then down, the planet a little larger in every new frame. Over weeks, by January it was a disk. By February it filled the narrow-angle camera. By early March it would not fit in the frame at all. The building filled up along with it. Jupiter Encounter was the first big planetary event JPL had run since the Viking landings, and the lab turned into something between a newsroom and a college dorm. Scientists flew in from all over the country and did not leave. People slept on couches in their offices. The imaging team worked in shifts around the clock in a room where new frames came up on monitors as they arrived, and a crowd would build up behind whoever was sitting at the console. Bradford Smith led the imaging team. He was an astronomer out of the University of Arizona. Dry, unflappable, and by all accounts the right person to have in that room, because the data was doing things nobody had planned for. What came into focus was not a planet in any sense the word had meant before. The Great Red Spot resolved into a storm with an interior. Clouds got dragged around its edges and pulled into filaments and swallowed. It turns counterclockwise and takes about 6 days to come around, and the Earth would fit inside it. Around it, the atmospheric bands ran in opposite directions at hundreds of miles an hour, with vortices spinning up along the shear lines and folding into each other. There were storms eating storms. The moons stopped being points of light and turned into places. And Voyager 1 was not flying past a planet. It was flying into a system. Jupiter's magnetic field is one of the largest structures in the solar system. Pushed toward the Sun, it extends millions of miles ahead of the planet, stretched away from the Sun by the solar wind. Its tail runs out past Saturn's orbit. If your eyes could see it from Earth, it would be several times the width of the full moon in the sky. That field is also a trap. Charged particles get caught in it, accelerated, and held in radiation belts thousands of times more intense than anything around Earth. A person flying the trajectory Voyager 1 flew would have taken a lethal dose. Not a dangerous dose, a dose that kills within days. The engineers had known this was coming and built for it. The radiation hardening from Chapter 4, with the large factor stacked on the worst-case estimate, was aimed squarely at this passage. Voyager 1 absorbed roughly 3 times what it was rated for. Things broke. The onboard clock drifted, which threw off the timing of commanded events, and some imaging sequences fired at the wrong moments. Certain instruments returned corrupted data through closest approach. The spacecraft came out the far side carrying damage it would never repair, and the flight team spent months afterward figuring out what had degraded and how to work around it. All of that went straight into Voyager 2, which was still 4 months behind. Its closest approach got moved farther out. Sequences were rewritten. The second spacecraft went through Jupiter's radiation environment with a scouting report written in real damage on real hardware. Now, the part of the Jupiter encounter that says the most about how Discovery actually works. Nobody thought Jupiter had rings. Saturn had rings. Saturn was the one with rings. That was settled. and there was no theoretical reason to expect a ring system at Jupiter, and no observation from Earth had ever hinted at one. But a member of the imaging team argued for spending one frame on a long exposure looking back toward the sun through the equatorial plane. The reasoning was thin, and everybody in the room knew it. Fine dust scatters light forward, toward the observer. When you look back at a light source through it, if anything was there at all, however faint, that geometry was the only way to catch it. One photograph. On a mission where every frame competed against every other frame for downlink time. Spending one on a hunch is a real cost. And there were people who thought it was a waste. They took it anyway. An 11-minute exposure of the space around Jupiter's equator on the 4th of March, 1979. There was a ring, thin, dark, made of fine dust, invisible from Earth and invisible from nearly every angle in space. It had been there the whole time. It took a spacecraft in exactly the right position, taking a picture that had almost been argued out of the plan. Our command has been running about 35 minutes now. It just crossed Jupiter's orbit. Everything in this chapter, the storms, the radiation, the ring, the entire encounter that put Voyager on magazine covers, sits inside the first half hour of a 23-hour trip, 3 days after closest approach. A navigation engineer at JPL pulled up an image of one of Jupiter's moons. She was not doing science. She was doing bookkeeping, checking the spacecraft's position by measuring where the moon sat against the background stars. She brightened the frame to bring out the faint ones, and there was something on the edge of that moon that had no business being there. Her name was Linda Morabito. She was 26, an optical navigation engineer at the Jet Propulsion Laboratory, and her job was to figure out exactly where the spacecraft was. That work is unglamorous and completely essential. You cannot pin down a spacecraft's position precisely enough from radio tracking alone at those distances. So the navigation team uses the cameras. Take a picture with a moon in it and some background stars. Measure the moon against the stars. Compare that to where the moon is predicted to be. And you can solve backward for where the camera must have been when the shutter opened. Do that over and over and you know your trajectory well enough to aim at Saturn. Morabito had come to JPL out of the University of Southern California. She was one of very few women doing technical work on the mission, and she was good enough at optical navigation that she had been handed the Voyager 1 post-encounter frames. On the 9th of March, 1979, 3 days after closest approach, she was working an image of Io. The stars she needed were faint, so she processed the frame to pull them up out of the background. Stretching the contrast that way blows out everything bright, which was fine, because she did not care about the bright parts. What came up on her screen was Io as an overexposed white disk, the stars she was after, and a bulge hanging off the upper left edge of the moon, something shaped roughly like an umbrella, standing a couple hundred miles above the surface, clearly separate from it. Her first thought was that it was an artifact. The tube cameras produced all kinds of defects, and everybody who worked with the data knew the catalogue of them by heart. Her second thought was that another moon was sitting behind Io and catching the light. She checked the ephemeris. Nothing was there. No object was predicted at that position at that time. She has described what happened next in interviews since. And the detail that stays with me is how ordinary it was. She got up and went to find her supervisor. Then she went and got people from the imaging team. Frames from the same sequence came out, and a second feature turned up on Io's disk. Somebody pulled the infrared data, which showed a spot on the surface, far hotter than anything around it. Io had a volcano erupting while the shutter was open. Here is why that mattered, and it is worth stating carefully, because the significance is easy to get wrong. Io is a little larger than our moon. Bodies that size lose their internal heat early. They form hot. They radiate that heat into space. And because the ratio of surface area to volume works against them, they cool all the way through. Our moon is geologically dead. Mercury is dead. Mars is very nearly dead. Every small, solid body anybody had ever examined was cold inside. And the reasoning behind that was sound and correct as far as it went. Io should have been a cold rock. Instead, it was the most volcanically active object in the solar system. More active than Earth. Throwing material a couple hundred miles up, the heat is not left over from formation. It is being generated continuously. Right now, by mechanical work, Io orbits close to Jupiter, and it is locked in a resonance with Europa and Ganymede that keeps its orbit slightly out of round. So as it goes around, the distance to Jupiter changes, and the enormous tidal force flexes the Moon. Io's solid surface rises and falls by up to 100 meters on every orbit. And every orbit takes about 42 hours. Bend a paperclip back and forth and the metal at the bend gets hot. That is the whole mechanism. Io is being kneaded by Jupiter's gravity. The friction of that kneading turns into heat. And the heat comes out as volcanoes. What makes this a good story rather than only a good discovery is the timing. 3 scientists had published a paper predicting exactly this. Stanton Peele, Patrick Casson, and Ray Reynolds worked out the tidal heating math and concluded that Io might show volcanic activity. Their paper appeared in Science on the 2nd of March. 1979. Voyager 1's closest approach to Io was on the 5th of March. Morabito found the plume on the 9th, a theoretical prediction and its confirmation, 1 week apart. After 4.5 billion years of nobody looking, and Morabito was not a planetary scientist. She was doing navigation bookkeeping on a frame that existed for no reason except to tell the spacecraft where it was. The single most consequential discovery of the Jupiter encounter came out of the least glamorous product of the mission. Found by someone whose assignment was to make sure the machine could aim itself at the next planet, which it did. 20 months later, at Saturn, the project faced the only decision in the whole mission that could not be undone. The decision got made years before the spacecraft arrived, which is how these things actually work. Nobody stands at a console watching Saturn grow and takes a vote. The trajectory has to be designed, argued over, and locked in early, because the course corrections that put you on it happen millions of miles out. Charles Colhase's team laid it on the table, and it was clean. Option 1. Fly Voyager, 1 close past Titan, Saturn's largest moon, and the only moon anywhere with a thick atmosphere. Option 2. Skip Titan, keep the spacecraft in the plane of the planets, and leave open the possibility of continuing on to Uranus and Neptune. You could not have both, and the reason is geometry. Titan orbits Saturn near Saturn's equatorial plane, which is tilted relative to the plane the planets travel in. To get close to Titan, Voyager 1 had to come in from above and dive through, and the encounter geometry that gave the best look at the moon also meant Saturn's gravity would throw the spacecraft up and out, roughly 35 degrees north of the ecliptic, climbing away from the disk of the solar system. After that, no more planets. Ever, Uranus and Neptune sit in the ecliptic. Nearly everything worth visiting sits in the ecliptic. A spacecraft leaving that plane is leaving the entire architecture of places to go, and Voyager 1 had no propulsion capable of putting it back. Its hydrazine is for pointing, not for changing course by 35 degrees, so the trade was 1 moon against 2 planets. They took the moon. The reasoning holds up. Titan was one of the most tantalizing objects in the solar system at that moment, and nobody had any idea what was under the haze. Ground-based spectroscopy had found methane. The atmosphere might be running organic chemistry at a scale nobody had seen anywhere else. There was talk of oceans, and Voyager 2 was still coming. It had fallen further behind on its slower path and had not yet reached Saturn. If Voyager 1 took Titan and got thrown out of the plane, Voyager 2 could stay in the plane and be retargeted for Uranus and Neptune, which is exactly what happened. And it is the reason the trade was defensible. The risk got distributed across 2 vehicles. Titan was the one that could not wait, because if both spacecraft passed it up, nobody was getting a close look at that moon for decades. On the 12th of November, 1980, Voyager 1 passed about 4,000 miles above Titan, closer than it came to anything on the entire flight. The pictures came back orange. That is the whole visual result. an orange ball with no features on it. The haze in Titan's upper atmosphere is a photochemical smog of hydrocarbon particles, thick enough and uniform enough that visible light does not get through. And the camera saw nothing of the surface at all. The most consequential close approach of the mission, the one that ended Voyager 1's planetary career permanently, produced a photograph you could reproduce with a spray can. Nobody in that room was happy about it. The instruments that were not cameras did much better. The radio science experiment worked by having the spacecraft pass behind Titan as seen from Earth. So the radio signal cut through the atmosphere on the way in and got bent and attenuated coming through. Measuring how the signal changed gave the atmospheric structure directly. The ultraviolet and infrared spectrometers read the composition. What came out of that was a real world. Titan's atmosphere is mostly nitrogen. Like ours, the surface pressure is about 1.5 times Earth's, which means standing there. The air would push on you harder than air does here. Surface temperature runs around 94 Kelvin, roughly 290 degrees below 0 Fahrenheit. And there is methane in that atmosphere in quantity. That combination of temperature and pressure puts methane near its triple point. It can exist as gas, liquid, and solid on the same world, the way water does on Earth, which raised the possibility of methane clouds, methane rain, and methane standing on the ground in pools. The Voyager data could not confirm any of it. It could only establish that the conditions permitted it. And that was enough to change the next 30 years of planetary science. 24 years later, the Cassini spacecraft arrived at Saturn carrying a probe called Huygens, built for the specific purpose of falling through Titan's haze. Because of what Voyager 1 had found and could not see, Huygens landed on the 14th of January, 2005, and sent back photographs of a plain scattered with rounded pebbles, cut by channels that had been carved by flowing liquid. Cassini's radar later mapped lakes and seas of liquid methane and ethane across Titan's northern latitudes, hundreds of miles across, all of it downstream of a decision made in 1980 to give up 2 planets for a flyby that came back orange. Saturn itself came the same day. Voyager 1 passed about 77,000 miles above the cloud tops, and the rings resolved into thousands of individual ringlets nobody had predicted. There was braided structure in the F ring. Small moons turned out to be acting as shepherds, holding ring edges in place with their gravity, and then it left. On the 12th of November, 1980, Voyager 1 completed the last planetary encounter it would ever have, 3 years and 2 months after launch. Every objective in the original mission plan met. The spacecraft was climbing out of the plane of the solar system on a hyperbolic trajectory at about 38,000 miles an hour, with a working camera system, a full set of instruments, most of its power supply, and nothing in front of it. Nobody had written a plan for what came next, because in the documents that got the program funded, there was no next for the following 9 years. The argument at JPL was about what to point the cameras at. The idea was not complicated, and it was not expensive. Point the cameras backward and photograph the solar system from outside it. Carl Sagan raised it in 1981, not long after the Saturn encounter, while he was serving on the Voyager imaging team. Turn the spacecraft, shoot a mosaic across the whole plane, and get every planet in one set of frames from a vantage point nothing had ever occupied. It took 9 years to get approved. The objections were real, and walking through them one at a time is the only honest way to tell this, because the standard version of the story skips straight to the photograph. The first objection was scientific value. There was none. Sagan never claimed otherwise. At that distance, the planets are a few pixels at most, and there is no measurement you can pull from them that Earth-based telescopes cannot get better. The imaging team had finite downlink and finite engineering attention, and every request competed against requests that would produce data somebody could publish. The second objection was hardware risk. To photograph the inner solar system from out past Neptune's orbit, the cameras have to look back toward the Sun, not at it, but near it, The Vidicon tubes were not built to handle direct sunlight, and there was legitimate concern that pointing them into that region could damage the detectors for good. That objection carried more weight than people remember now, because the cameras were still the mission's most valuable instrument, and nobody wanted to be the engineer who ruined them for a picture with no science in it. The third objection is the boring one that actually delays things. The team was busy. Voyager 2 was still working its way outward, and the flight team was consumed with the Uranus encounter in 1986 and then Neptune in 1989, building a new command sequence, calibrating the pointing, and running a mosaic takes engineers. And those engineers had assignments, so the request sat. It got raised again and deferred again. Sagan kept bringing it up in meetings, and the answer kept being, not now. Voyager 2 passed Neptune in August of 1989. The planetary phase of the entire program was over. The cameras had nothing left to photograph and were scheduled to be powered down to save electricity. Sagan pushed one more time. Richard Truly, the NASA administrator, backed it. On the 14th of February, 1990, Voyager 1 executed the sequence. 60 frames, covering a wide swath of the plane of the solar system, taken from about 3.7 billion miles out. The mechanics of that shoot are worth having. The spacecraft had to hold its pointing steady enough for the exposures. That meant the thrusters firing in short pulses and then letting the vehicle coast, because a thruster firing mid-exposure smears the image. Some frames use the narrow-angle camera to capture individual planets, and the geometry had to be exact, because the targets were a few pixels wide and the pointing knowledge at that range was not perfect. 6 planets came out: Venus, Earth, Jupiter, Saturn, Uranus, Neptune. 3 did not. Mercury sits too close to the Sun and was lost in the glare. Mars was on the wrong side and too faint against the scattered light. Pluto was too small and too dark to register at all, and Earth came out as less than 1 pixel. Not 1 pixel. Less. The planet did not fill a single detector element. Its light spread across a fraction of 1, and the reason you can pick it out of the image at all is that it happened to land inside a band of scattered light. Those beams in the famous frame are not sunbeams. They are an optical artifact, sunlight bouncing around inside the camera assembly, off the edges of the baffles and the lens elements, throwing streaks across the field. Earth landed in one of them by coincidence of geometry, a lens flare, and a planet smaller than a rounding error, in a photograph that had been argued about for 9 years and had no scientific purpose. The mosaic came down over the following weeks. The data rate at that distance was slow, and the frames arrived in pieces, and the team assembled them as they came. 6 weeks after the last frame was received, the flight team sent the command to power down the camera system. They did not do it only to save electricity, though that was part of it. There was another reason, and it is the one that almost never gets mentioned. The cameras were not simply switched off. The ability to use them got taken apart. Voyager 1 runs on 3 pairs of computers, and the one that matters here is the Flight Data Subsystem. It formats every measurement the spacecraft makes, packages it for transmission, and runs the operating modes for the instruments. Its memory is small enough that the number is worth saying out loud. Each of its 2 units holds 8,192 words, not megabytes. Words. All 3 computer pairs on that spacecraft, added together, run on less memory than a single photograph on your phone takes up. Camera operation occupied a meaningful share of that. The imaging software had to be resident while there was imaging to do. Once there was not, that memory was worth more as space for something else. So over the years that followed, the camera software got overwritten. Not carelessly. It was a resource decision on a machine where every resource was scarce, made by people who had no reason to think anyone would ever want it back. The knowledge went the same way. The engineers who knew how to build and validate an imaging sequence moved to Galileo, or to Cassini, or to the Mars programs, or they retired. The ground software that generated camera commands stopped being maintained, and eventually stopped running on any computer NASA still owned. The calibration files, the pointing models, the procedures for warming the optics before an exposure. All of it decayed, the way institutional knowledge decays when nobody is using it. JPL has been asked about this many times. Could you turn the cameras back on? The answer they give is that even if there were power to spare, and there is not, the capability no longer exists on the spacecraft or on the ground. You would have to rebuild it from documentation, in assembly language, for hardware that has been running in vacuum for 4 decades, and load it into a computer that has since suffered a memory failure. Nobody is going to spend what is left of this mission on that. The last photograph any human being will ever receive from Voyager 1 was taken on the 14th of February, 1990. The spacecraft went blind at the age of 12. It has been flying for 36 years since. Bolted to the side of it, the whole time, is a copper disc carrying 115 pictures of Earth. The spacecraft cannot see anything, and it is still carrying photographs. What it did keep were 5 other senses, and none of them involve light in the way you mean the word. The magnetometers measure magnetic field strength and direction. There are 4 of them. 2 mounted out on a boom extending 43 feet from the body. That far out because the spacecraft's own electronics generate fields that would swamp the readings. The cosmic ray subsystem counts high-energy particles and sorts them by energy and species. It tells you what is hitting the spacecraft and how hard. The low-energy charged particle instrument does the same work at the other end of the energy scale. For the slower particles that make up the solar wind and its interstellar equivalent, the plasma science instrument measures the density, speed, and temperature of the ionized gas the spacecraft is flying through. Hold on to this one. It comes back later, and not in a good way, and the plasma wave subsystem listens. 2 antennas, 33 feet each, forming a V, measuring oscillating electric fields in the plasma around the spacecraft. Plasma is not quiet in the electromagnetic sense. It rings. It sloshes. It carries waves the way water does. And this instrument was built to catch them. So after 1990, everything Voyager 1 would ever discover arrived as numbers. Counts per second. Field strength in nanoteslas. Particle energy. No image. No visual confirmation of anything. No way for a person to glance at the data and immediately see what it meant, which is a harder way to do science, and a much harder way to know where you are. The question in front of the mission after 1990 was a question about position, and it had no obvious answer. Voyager 1 was headed for the boundary of the Sun's influence, a place nobody had been and nobody could see. And the plan for detecting the crossing depended on instruments reading invisible quantities in a region where the models disagreed with each other by a factor of 3. One of those instruments had already failed, 10 years earlier, and there was a second spacecraft out there, launched 16 days sooner, headed in a completely different direction, running the same experiment with a different set of working hardware. Before we follow Voyager 1 across that boundary, it is worth knowing what happened to its twin, because the comparison between them is the closest thing this mission has to a control group. 2 spacecraft came out of that clean room in Pasadena. Same drawings, same technicians, same wiring harness, built side by side and finished within weeks of each other. 49 years later, they are in completely different situations, and the difference has almost nothing to do with how well they were built. Voyager 2 got the Grand Tour. That is the part most people have backward. The mission that got cancelled in 1971, the 4-planet run that Gary Flandreau found on graph paper, got flown after all. It just got flown by the spacecraft nobody was watching. Once Voyager 1 committed to Titan and threw itself out of the plane, Voyager 2 was the only vehicle left in the ecliptic, with a working camera and enough fuel to keep going. So the flight team retargeted it. Jupiter in 1979, Saturn in 1981, and then a long, quiet cruise, Uranus in January of 1986. Neptune, in August of 1989. Voyager 2 is the only spacecraft that has ever visited either of those planets. Not the only one recently. The only one, period, in the history of the species. Every photograph you have ever seen of Uranus as a featureless blue-green ball, and every photograph of Neptune with its dark storm, came off one vehicle during one flyby, and there is no funded mission to go back. The Neptune encounter is worth a beat. Because of the timing, Voyager 2 passed Neptune on the 25th of August, 1989, and the closest approach took it about 3,000 miles above the planet's north pole. That is very close. Then it swung down past Triton, Neptune's largest moon, and found geysers of nitrogen venting from the surface of a world at 38 degrees above absolute zero. 3 weeks later, the Berlin Wall was still standing. By the time the last of the Neptune data finished coming down, it was not. The planetary phase of the American space program's greatest run ended in the same season as the Cold War that funded it. Now the divergence. Voyager 1 got thrown north out of the ecliptic by Saturn's gravity in 1980. Voyager 2 got thrown south by Neptune's gravity in 1989, about 48 degrees below the plane. That single difference in geometry decides how each spacecraft is operated today. Voyager 1 sits high in Earth's northern sky. Goldstone and Madrid can see it. Canberra, in the southern hemisphere, has a poor view. Voyager 2 sits deep in the southern sky. Canberra can see it. Nothing else can, which means every command sent to Voyager 2 for the last 37 years has gone out through one antenna on one continent. Deep Space Station 43, outside Canberra, Australia. It is the only dish on Earth with a transmitter powerful enough and positioned correctly to talk to that spacecraft. In March of 2020, DSS 43 went offline for a major upgrade. New transmitters, new cooling, new electronics on hardware that had been in service since 1973. The work took 11 months. For 11 months, NASA could listen to Voyager 2 and could not talk to it. The spacecraft kept sending. Engineers watched the telemetry come down through the smaller antennas at Canberra and confirmed it was healthy. And there was no way to send it a single instruction. If something had gone wrong in that window, the team would have watched it happen and been unable to respond. Nothing went wrong. The dish came back online in February of 2021, and the first command they sent was a test. The spacecraft acknowledged it. Then there are the failures. And this is where the two spacecraft really part ways. Voyager 1's plasma science instrument stopped returning useful measurements early in the mission and was finally powered down on the 1st of February. 2007. Voyager 2's plasma science instrument kept working. It ran for another 17 years, all the way through the heliopause crossing, and it was shut off on the 26th of September, 2024. Purely to conserve power. It was still functioning on the day they turned it off. That difference is why Voyager 2's boundary crossing in 2018 produced clean, direct plasma density measurements, while Voyager 1's crossing in 2012 turned into a 13-month argument. Same design, same builders, one instrument aged out early and the other did not. And nobody has ever fully explained why. Voyager 2 also lost its primary receiver in 1978, a year after launch. The backup receiver had a failed component in its tracking loop, which means it can only hear a very narrow band of frequencies, and that band shifts with the temperature inside the spacecraft. Since 1978, every command sent to Voyager 2 has had to be transmitted at a frequency calculated in advance to account for how warm the receiver will be when the signal arrives. 48 years of talking to a spacecraft that can only hear you if you guess its body temperature correctly. Both vehicles are now in interstellar space. Voyager 1 crossed in 2012. Voyager 2 in 2018. At a different distance. In a different direction. Which by itself was a significant scientific result, because it showed the heliosphere is not the same size everywhere. Voyager 1 is farther, and it is pulling away. Because it left faster and it never slowed down. It will always be the farthest. Voyager 2 cannot catch it, and neither can anything else humanity has launched. New Horizons is going slower and started later. Pioneer 10 and 11 stopped transmitting decades ago and are falling behind. Nothing on any drawing board is going to change that in the working lifetime of anyone reading a budget today, which brings us back to the boundary Voyager 1 had to cross first, and to the fact that it went in there with the one instrument built to detect it already dead. Most people have the wrong picture of where the sun ends, and the wrong picture is not anybody's fault. It comes from the diagram. You learn the solar system as a set of orbits. Sun in the middle, planets at increasing distances, and past the last planet you are out. That diagram is about gravity and about objects, and it leaves out the thing that actually defines the sun's territory. The sun leaks. Its outer atmosphere is so hot that its own gravity cannot hold on to it. Gas boils off continuously and flows outward in every direction at somewhere between 800,000 and 2 million miles an hour. That is the solar wind, and it is a physical flow of ionized hydrogen and helium, thinner than anything you would call a gas on Earth, moving fast, and it never stops. That flow inflates a bubble. Outside the bubble is interstellar space, which is not empty either. It has its own gas, its own magnetic field, its own population of particles blown off dying stars and accelerated across the galaxy by supernovas. That material pushes inward. Solar wind pushes out. Interstellar medium pushes in. Wherever those two pressures balance, you get a surface, and everything inside that surface is the heliosphere. That is the sun's actual territory, a weather system, not a set of orbits, and it is enormous. Every planet is inside it. Every comet you have ever heard of is inside it. The entire Kuiper belt, out past Neptune, sits inside it with room to spare. Voyager 1 crossed Pluto's orbital distance in 1990, the same year the cameras went dark, and nothing happened. No change in the environment. The spacecraft was still flying through solar wind, still inside the sun's atmosphere in every functional sense, still surrounded by material that had left the sun's surface a few months earlier. Getting out takes 4 stages, and the names get mixed up constantly. So here they are in order. The termination shock comes first. The solar wind is moving supersonically, which in a plasma means faster than waves can travel through it. When it starts to feel the pressure of the interstellar medium ahead, it cannot slow down smoothly. The same way a supersonic aircraft cannot smoothly push air out of the way. It shocks. The flow drops abruptly from supersonic to subsonic. The gas heats and compresses, and the direction of flow begins to turn. The heliosheath comes next. That is the region past the shock, where slowed and heated solar wind piles up and gets deflected sideways, flowing around toward the tail of the heliosphere, the way water flows around a boulder. It is turbulent, and it turned out to be billions of miles thick. The heliopause is the actual boundary, the place where the solar wind stops and the interstellar medium begins. Past it, the spacecraft is flying through material that never came from our sun. The 4th boundary is gravitational, and it is a completely different question. The sun's gravity holds objects far past the heliopause. The Oort cloud, the shell of icy bodies that supplies long-period comets, is thought to begin somewhere around 2,000 times the Earth-Sun distance and extend outward from there by orders of magnitude. So here is the precise statement, and it is worth getting right, because it gets mangled in nearly every headline written on the subject. Voyager 1 has left the heliosphere. It is in interstellar space, flying through material from between the stars. It has not left the solar system in the gravitational sense, and will not for a very long time. It needs roughly 300 more years just to reach the inner edge of the Oort cloud, and something like 30,000 years to pass beyond the outer edge, as it is conventionally estimated. Both statements are true at once, and neither one is a technicality. Now, the practical problem the mission faced through the 1990s, nobody knew where the heliopause was. The heliosphere is not a fixed object. It inflates and contracts as the sun's output varies over its 11-year cycle. Its shape depends on the interstellar magnetic field, which had never been measured directly by anything. Models published in that era put the boundary anywhere from about 50 times the Earth-Sun distance to well past 150. That is a factor of 3. On a mission, losing 4 watts a year. A factor of 3 is the difference between arriving with instruments running and arriving as a dead object. Ed Stone was asked about it repeatedly in those years, and his answer was consistent and unsatisfying. They did not know. They would find out when they got there. And the only way to find out was to keep the spacecraft alive long enough to arrive. And there was the other problem. The instrument designed to measure the quantity that defines the boundary had failed. Voyager 1's plasma science instrument, which reads the density of the plasma the spacecraft is flying through, had degraded early and was returning nothing useful. Plasma density is the cleanest indicator of which side of the heliopause you are on, because the interstellar medium at that distance is far denser than the solar wind. Voyager 1 was flying toward the most significant boundary crossing in the history of the space program, without the one instrument built to detect it. The first boundary came in December of 2004, and the spacecraft had to be argued into it. Voyager 1 was about 94 times the Earth-Sun distance out when the particle instruments recorded a sharp change. The count of low-energy charged particles jumped. The magnetic field strength went up. Both are what you expect at a termination shock, where the solar wind slams from supersonic to subsonic, compresses, and heats. Without plasma measurements, nobody could watch the flow speed drop directly. They were reading the consequences of a slowdown instead of the slowdown itself, and there had already been a false alarm. In 2002, the same instruments showed a similar signature, and a group of scientists published a paper announcing that Voyager 1 had crossed the shock. Another group published a paper saying it had not. The argument ran for 2 years in the journals before the 2002 event got reclassified as the boundary itself moving outward, past the spacecraft, and then retreating back inward. The heliosphere breathes. That was the lesson of 2002, and it made everyone cautious about the next one. By 2005, the 2004 crossing was generally accepted. Voyager 1 was in the heliosheath. The turbulent region passed the shock, and now the real waiting started. Because nobody knew how thick that region was, the predictions said 1 or 2 years to cross it. It took 8. What the spacecraft found in there was strange enough to generate its own vocabulary. The solar wind slowed, then slowed further. And then around 2010, it stopped moving outward entirely. The radial flow went to 0. The plasma was being turned and pushed sideways, flowing around the obstacle ahead. And Voyager 1 was sitting in a place where the sun's wind had quit going anywhere at all. Then in 2011, the particle readings started doing something new. Solar particles began leaking outward along magnetic field lines, and galactic cosmic rays began leaking inward, as though the boundary had turned porous. Somebody on the team called it the magnetic highway, and the name stuck. Then came the 25th of August, 2012. Over the course of a few days, 2 counters went in opposite directions and both went hard. Low-energy particles originating from the sun dropped to essentially 0. Galactic cosmic rays. The high-energy particles from the rest of the Milky Way that the heliosphere normally shields us from jumped by about 9% and stayed up. That is the signature. Solar particles gone. Galactic particles arriving. By any reasonable reading, Voyager 1 had crossed the heliopause. The team could not say so. The problem was the magnetic field. Every model predicted that when a spacecraft crossed the boundary, the direction of the magnetic field would swing. Because the sun's field and the interstellar field point different ways, and the heliopause is where one gives way to the other. That swing was the confirming evidence everyone had been waiting 30 years for. The magnetometer showed the field getting stronger. It did not show the direction changing. So there were 2 possibilities. Either Voyager 1 had crossed into interstellar space, and the field direction happened to be aligned in a way nobody had predicted, or the spacecraft was still inside the heliosphere, in some structure nobody had modelled, and the particle changes meant something else. Papers came out taking both positions. One group proposed a new region and called it the heliosheath depletion layer. Another proposed a magnetic structure at the boundary that could explain the alignment. The mission's own scientists were split down the middle. Ed Stone would not announce a crossing. He had been project scientist since 1972. 40 years on this mission at that point, and the single biggest result of his career was sitting in front of him with one piece of evidence missing. His position was consistent, and he repeated it to anyone who asked. They would announce when they had data that did not depend on interpretation. For 13 months, the most significant boundary crossing in the history of spaceflight sat unannounced, because an instrument that would have settled it in an afternoon had been dead since the early years of the mission. Then the sun did them a favour. In March of 2012, months before the crossing, the sun threw off a large coronal mass ejection. That kind of disturbance travels outward through the solar wind, and when it eventually reaches a boundary region, it pushes on whatever plasma is there and sets it oscillating. It reached Voyager 1 in April of 2013, 13 months in transit, and the plasma wave subsystem, with its two 33-foot antennas, heard the plasma around the spacecraft start to ring. Here is why that solved everything. A plasma has a natural oscillation frequency. Disturb it and the electrons slosh back and forth against the ions at a rate that depends on exactly one thing: the density of electrons. Denser plasma rings at a higher pitch. The relationship is a simple equation with no free parameters in it, and it has been understood since the 1920s. So a working plasma wave instrument can substitute for a dead plasma density instrument, as long as something comes along and hits the plasma hard enough to make it ring. Don Gurnett at the University of Iowa had built the plasma wave subsystem and had been its principal investigator since before launch. He was 73 years old in 2013 and had been waiting on this measurement for 36 years. He and his colleague Bill Kurth read the frequency of the oscillation and ran the arithmetic. It came out around 80,000 electrons per cubic meter. Inside the heliosphere at that distance, the expected value was roughly 1,000, 40 times denser, and squarely in the range predicted for the interstellar medium. Then they went back through the archive and found an earlier, weaker oscillation from October and November of 2012 that nobody had been able to interpret at the time. Same calculation, slightly lower density, consistent with the spacecraft having crossed a bit earlier and the medium being marginally thinner right at the boundary. Working backward from both measurements put the crossing on the 25th of August, 2012. NASA announced it on the 12th of September, 2013, 13 months late. And right. Gurnett described the moment he saw the frequency in the data as the point where he knew, and he was blunt about what it meant for the mission. They had finally left the bubble. There is one more thing about that oscillation. The frequency was around 2.25 kilohertz. That sits in the middle of the range of human hearing. Not near it. Inside it, the top note on a piano is a little over 4 kilohertz. Gurnett's team at Iowa had been converting plasma wave data into sound files since the 1970s, because a trained ear picks structure out of a spectrogram faster than an eye does, so they ran it through a speaker. Be precise about what is happening here, because this gets described badly almost everywhere, and the accurate version is better than the loose one. There is no sound in space. Sound is a pressure wave in a medium dense enough to carry it, and the interstellar medium is a hard vacuum by any standard you would use in a laboratory. If you were out there with Voyager 1 and you had ears and could somehow survive, you would hear nothing at all. What the plasma wave subsystem measures is an oscillating electric field. Electrons in the plasma displace, get pulled back by the ions they left behind, overshoot, and oscillate. That oscillation produces a varying voltage across the two antennas, and the instrument records the voltage. The frequency of that electrical oscillation happens to fall in the same numerical range as audible sound. Take the voltage record and feed it to a speaker instead of a plotter, and you get something you can hear. It is a translation. The physics is electrical, the output is acoustic, and the number in the middle is the same number. Gurnett's group at Iowa had been doing this since the 1970s, and they were good at it. They found structures in Jupiter's magnetosphere and Saturn's radio emissions by listening to them. Because the human auditory system is extraordinary at pulling a signal out of noise, better than most software, and considerably faster. What came out of the April 2013 data was a rising tone, a whistle that climbs in pitch over a couple months of data compressed into a few seconds. And the climb is the physics. As the shock front from the solar storm moved past the spacecraft and compressed the plasma, the density went up, and the ringing frequency went up with it. That sound is the confirmation that Voyager 1 left the heliosphere. It is not a metaphor for the confirmation. It is the data. Then there is the part that came later, and it is stranger. In 2021, a graduate student at Cornell named Stella Ocker was working through years of plasma wave data looking for the events, the loud ones, the solar shocks that let you take a density measurement. She found something in between them, running underneath the events. In the quiet stretches where nothing was happening, there was a faint narrowband signal at a nearly constant frequency. It was weak. It was persistent. It had been sitting in the data since 2017. And nobody had picked it out, because everybody had been looking for the loud things. It was the interstellar medium ringing on its own. The plasma out there is being disturbed continuously by something. Most likely thermal motion combined with the turbulence that runs through the galaxy at every scale. And it hums at its natural frequency without needing a solar storm to set it off. The scientific consequence is direct, and it is large. Before this, measuring interstellar plasma density meant waiting for the sun to throw something outward, and then waiting a year or more for it to arrive. Density measurements came a few times a decade. When the sun cooperated, the persistent hum gives density continuously, which means the spacecraft can now track how the density changes as it moves. And it does change. The medium is not uniform. It gets denser in some places and thinner in others. Structure at scales nobody had any way to detect before. Ocker described it the way you would expect a graduate student to describe finding something in an archive that senior people had been walking past for 4 years. It was faint and monotone, and it had been there the whole time. An instrument that measures one thing became the replacement for an instrument that died in the early 80s. 40 years later, because somebody went looking in the quiet parts of the data, Voyager 1 lost its eyes in 1990. What it has now is a pair of antennas in a V, listening to a medium nothing else has ever sampled. At a distance where every other measurement humanity has of interstellar space comes from watching starlight pass through it from 15 billion miles away, on the wrong side of the boundary. That instrument is one of the 2 still running tonight. Everything the spacecraft was built to do. It finished in 1980. Everything it has done since. It did, with hardware nobody designed for the job, in a place the design never contemplated, operated by people who in some cases had not been born when the original sequences were written. Our command has been travelling about 16 hours now. It crossed the heliopause somewhere in the last hour. Out where the counters flipped in 2012. 7 hours left. And in those 7 hours, on the ground, there is nothing to do but wait and read. Which on this mission means something more literal than it sounds. Because a lot of what they need is on paper. In a cabinet. Typed on a machine that has not been manufactured in 40 years. The Voyager office at JPL is in a building up against the foothills. On a campus where some of the structures date to the 1940s, and the parking is still a problem. The room does not look like mission control in a movie. Desks. Monitors. A whiteboard with somebody's handwriting on it. A coffee maker that has outlasted several project managers. Fly, both spacecraft and the entire team fits at 2 conference tables with chairs left over. What is in that office? And in the storage nearby? Is the reason this spacecraft is still alive? Start with the software, because it is the part that makes working engineers wince. Voyager runs 3 pairs of computers, and all of them are programmed in assembly language for architectures that were built for this mission and have never existed anywhere else. There is no compiler. There is no development environment. There is no emulator anybody will point to and call a faithful model of the flight hardware in its current condition, because the flight hardware has been modified by command from the ground hundreds of times across 49 years, and every one of those modifications changed the state of the machine. To write a command for Voyager, you have to know the computer at the level of individual memory addresses. What is stored where? What depends on what? What a change at one location will do 3 subroutines away. That knowledge was never fully written down in one place. It lived in people's heads. Some of it made it into documentation. And that documentation exists. And it is on paper. Typed pages in binders. Schematics drawn on vellum. Interoffice memoranda from the 1970s explaining why a particular capacitor was chosen over another. Filed in cabinets. Most of it never scanned, because scanning it was never anybody's funded assignment. Suzanne Dodd has talked about this more than once, and her description does not vary much. When she came back to Voyager in 2010, after 20 years away, part of the job was finding out what the lab still had. The answer was boxes, documents in cabinet, handwritten notes in the margins, material that had to be tracked down because the person who understood a given subsystem had retired to another state or had died. Here is what that looks like as an afternoon. An engineer needs to know why a particular register on the attitude control computer gets set the way it does during a specific mode change. The behavior is not documented in anything on the network, so somebody walks down the hall to a room with flat files and cabinets in it and starts opening drawers, looking for a memo from 1976 that may or may not exist, written by a man who left the lab in 1983. Sometimes it is there. Sometimes what is there is a schematic with a note in pencil in the margin. In handwriting, nobody in the building recognizes, and the note answers the question. Sometimes it is not there, and the next step is a phone call. There is an informal list of retired Voyager engineers, some of them in their 80s, who still take those calls. Several have been brought back as consultants over the years, on and off, when a problem needed somebody who remembered. Ed Stone held the science side of this together for 50 years. He took the project scientist job in 1972 at 36 and stepped down in 2022 at 86. He gave press conferences for the Jupiter encounter, the Saturn encounter, the Uranus encounter, the Neptune encounter, the termination shock, and the heliopause crossing. 6 decades of the same mission and the same careful, unexcitable delivery. He died in June of 2024, at 88, 2 months after the team recovered the spacecraft from the failure we are about to get to. Now the ground infrastructure, which almost nobody covers and which constrains everything. Voyager 1 can only be heard by a 70-meter dish. There are 3 of them. Goldstone in California, Robledo outside Madrid, Tidbinbilla outside Canberra. They were built in the 1960s and 70s. They are being refurbished on a rolling schedule, which means at various points one of them is offline for months, and the coverage has to be absorbed by the other 2. They also serve every deep space mission NASA operates. Mars, orbiters, and rovers. Pseucha, Europa Clipper, New Horizons, UNO, plus support for partner agencies. Every mission submits requests for antenna time, and a scheduling process allocates it. Voyager competes for that time the same as everybody else. And Voyager's requirements are not modest, because the signal is faint enough to need the biggest dish for hours at a stretch. There is a geometric constraint on top of that, and it traces back to 1980. The Titan flyby through Voyager 1 about 35 degrees north of the plane of the planets, which puts it high in Earth's northern sky. Goldstone and Madrid have the good view. Canberra does not. Voyager 1 is primarily a northern hemisphere target, and the load falls on 2 of the 3 stations. So the operating environment is this: aging hardware on both ends of the link, 3 antennas shared across a fleet, a team small enough for a conference room, an archive that lives partly in filing cabinets and partly in the memory of people in their 80s. And on the 14th of November, 2023, That team had to repair a computer they could not see, could not touch, could not restart, and could not test on. The flight data subsystem is the spacecraft's reporter. Every instrument reading, every temperature, every voltage, every status flag goes through it. It formats all of that into a data stream and hands the stream to the telemetry system for transmission. On the 14th of November, 2023, it started sending the same block of bits over and over, not random noise, a repeating pattern, which is worse in a way, because random noise points to a transmission problem, and a repeating pattern points to a computer that is running and producing the wrong thing. Whatever was happening inside the machine. Everything else looked normal. The carrier was steady. The spacecraft responded to commands. Attitude control was holding, which meant the antenna was still aimed correctly, and the thrusters were still firing on schedule. Voyager 1 was healthy, and it had lost the ability to describe itself. The first move tells you how this kind of work goes. They did nothing risky. The instinct in a failure is to act. The Voyager team has a rule that has kept both spacecraft alive for decades, which is that you do not send a command whose consequences you do not fully understand, and you especially do not do it when you cannot see the machine's state. A blind reset of a computer in an unknown condition is how a recoverable problem becomes a dead spacecraft. So they spent weeks characterizing, send a low-risk command, wait 46 hours, look at what came back, form a theory, send another one, 46 hours. That is the tempo of the entire investigation. In a normal engineering job, you might run 20 tests in a day. Here you get one test every 2 days. And each one costs a scheduled block of time on a 70-meter antenna that 6 other missions also wanted. Picture what that does to a work week. You transmit on a Monday afternoon. You go home. Tuesday there is nothing to do about it. So you work other problems and think about it in the car. Wednesday morning the pass comes down, and you find out that your theory was wrong, which is the most likely outcome. And now you have spent 2 days to eliminate one possibility out of a list that keeps getting longer. Then you do it again. By January, the team had narrowed it to the flight data subsystem. By February, they were reasonably sure the problem was corrupted memory. What they could not do was see the memory, because the thing that would normally report the memory contents was the thing that had failed. In early March, they tried something clever. They sent what the team called a poke, a command telling the FDS to run a different software sequence than the one it had been running, on the theory that if the problem was localized, a different sequence might route around it and produce something readable. The response came down on the 3rd of March. It was not the normal telemetry format, and it was not the stuck pattern either. It was something else. An engineer at the Deep Space Network looked at that signal, recognized that it contained a readout of the entire FDS memory in an unusual format, and worked out how to decode it. Now they had a dump. The complete contents of the computer, address by address. For the first time since the failure, the next step is the one that only works because of the cabinets from the last chapter. They compared that dump against the record of what should have been in that memory. That record exists on the ground because somebody in the 1970s started documenting every patch and every load. And everybody since kept doing it. The comparison found the failure. About 3% of the FDS memory was corrupted. A single chip holding part of the computer's software had stopped working. The likely cause is either a cosmic ray strike or ordinary wear on a component that has been powered continuously for 46 years. And there is no way to tell which from here. That chip is not coming back. There is no repair. So the problem became a relocation problem. And this is where it gets hard. The code that lived on the dead chip had to be moved somewhere else. But FDS memory is 8,192 words total. And after 46 years of patches and additions and workarounds, there was no single unused block anywhere in it large enough to hold the displaced code. The solution was to break the code into pieces and scatter them into whatever gaps existed. That sounds straightforward, and it is not. For one reason. Code refers to itself. A jump instruction points to an address. A subroutine call points to an address. A data table lookup points to an address. Move a chunk of code to a new location and every reference to it, anywhere in the entire program, is now pointing at the wrong place. So every piece had to be relocated, and then every reference to every piece, throughout the whole 8,000-word program, had to be found and corrected, in assembly language, for a custom architecture with no development tools, on a program that has been modified by dozens of engineers across 5 decades, a number of whom are dead, and there was nowhere to test it. No flight spare in the right configuration. No emulator anybody trusted for this. The first execution of the modified code would be on the actual spacecraft, 15 billion miles away, and if it failed in the wrong way, the spacecraft might not be able to tell them how it failed. They did it in stages. Move one piece. Wait. Verify. Move the next. On the 18th of April, 2024, they transmitted the first relocated section, the code responsible for packaging engineering data. The signal took about 22.5 hours to reach the spacecraft. Then the team went home. Whatever happened in that computer happened on a Thursday night, in silence, with nobody watching, 15 billion miles from the nearest person who cared about the outcome. If it worked, they would know in a day. If it did not, they would also know in a day, and the mission might be over. On the 20th of April, 2024, the telemetry came down readable for the first time in 5 months. Temperatures, voltages, status flags, the spacecraft describing itself. There is a photograph from the Voyager office that afternoon. A dozen or so people crowded around a screen, some of them with their hands up, one of them holding a phone, and a sheet cake on the table behind them. It looks like every office celebration you have ever been in. And what they were celebrating was talking their way through a hardware failure on a machine that left Earth during the Carter administration. The remaining sections, the ones handling science data, got moved over the following weeks. By the 22nd of May, 2 of the 4 operating science instruments were returning usable data. By the middle of June, all 4 were. 5 months from the failure to the first readable engineering data. 7 months to full science return. That is a fast repair. Given that every iteration cost 2 days of waiting, and the machine being repaired had been running longer than most of the people repairing it had been alive. Ed Stone died about 6 weeks after the science data came back. He had been project scientist when that computer was designed. The spacecraft went back to work, and it is still working. While all of that was going on, something else was getting worse, on a schedule nobody could stop. Start with what happens if this one fails, because the stakes here are absolute and they are easy to miss. Voyager 1's high-gain antenna has to point at Earth within about 1/4 of a degree. That is roughly a dime held at arm's length. Inside that cone, the deep space network can pull the signal out of the noise. Outside it, the signal drops below threshold and the spacecraft is gone. Not damaged, not dead, gone. Still flying, still generating power, still running its instruments, still transmitting into empty space, with nobody able to hear it and no way to tell it to turn back. Holding that pointing is the job of the attitude control thrusters. There are 16 of them on Voyager 1, arranged in 2 complete sets of 8. 1 primary and 1 backup. Each is small. The whole assembly of a single thruster is about the size of your fist, and the nozzle itself is smaller than that. They burn hydrazine, which is a monopropellant. No oxidizer needed. It flows over a catalyst bed, decomposes violently, and produces hot gas out the nozzle. No ignition system. No mixing. No moving parts past a valve. It is the simplest reliable thruster design there is, which is exactly why it flew. The spacecraft is stabilized on 3 axes. It finds the sun with sun sensors and finds a reference star with a star tracker. For most of the mission, a bright southern star called Canopus, and it holds its orientation against those 2 references. When it drifts outside the deadband, A thruster fires a short pulse and pushes it back. A pulse is measured in milliseconds. It is a tap. The spacecraft has been tapping itself back into alignment for 49 years. The cumulative number is what gets you. Each thruster branch has fired on the order of hundreds of thousands of times. Across the mission, the total runs into the millions of individual pulses. Every one of them leaves something behind. Hydrazine decomposition is not perfectly clean. Trace amounts of silicon dioxide, which is essentially glass, deposit inside the propellant inlet tubes. A tiny amount per firing, far too small to measure in any laboratory test of reasonable duration. Multiply it by hundreds of thousands of firings across 5 decades and the tubes narrow. The inlet openings started at about 0.01 inches across. Recent measurements put some of them down around 0.0015 inches. And still closing. When a tube shuts far enough, that thruster branch stops delivering propellant and stops working. The hydrazine tank is not the limiting factor. There is still fuel in it. The plumbing is the limiting factor. And it is closing on a one-way schedule that nothing reverses. So the history of this mission's thrusters is a sequence of moves down the bench. The original attitude control branch ran from launch. As its performance degraded, the team switched Voyager 1 to the backup attitude control branch. That branch then accumulated its own firings and its own deposits. In 2017, they went looking for something else. Voyager 1 carries a second set of thrusters called TCM thrusters for trajectory correction maneuver. They were built for course corrections during the planetary phase. They are larger, and they had not been fired since the 8th of November, 1980, 4 days before the Titan encounter. 37 years of sitting cold in vacuum. The question was whether they would fire at all, and whether they could be repurposed for attitude control, which is not what they were designed for. Attitude control wants short, precise pulses. These were built for sustained burns. The team went to the documentation. This is the paper archive from Chapter 17, doing the job it exists for. They pulled the original design specifications and the operating procedures, written by engineers who had mostly retired decades earlier, and they found what they needed to know about how those thrusters behave in short pulse mode. Todd Barber was the propulsion engineer on it. He has described the mood in the room going in, and it was not confidence. Nobody knew whether hardware that had been dormant since 1980 would respond at all. They wrote a command sequence, checked it, and sent it on the 28th of November, 2017, 19 hours and 35 minutes later. The signal arrived. 4 thrusters that had not fired since the Carter administration pulsed for 10 milliseconds each. 19 hours and 35 minutes after that, the telemetry came back to Pasadena. They worked perfectly. Voyager 1 switched to the TCM thrusters for attitude control in January of 2018, and that switch bought the mission an estimated 2 to 3 additional years. Then, in 2025, they went back for one more. By then, the TCM thrusters had been running for 7 years and were building up their own deposits. The remaining option was a set of thrusters that had been written off back in 2004, when a small heater circuit inside them failed. Without the heater, the assessment at the time was that the thrusters could not be used safely, and the team moved on and did not revisit it. 21 years later, engineers went back and re-examined that call. The reasoning was that the original failure might have been in a power switch rather than in the thruster circuit itself. Flip the switch back, and the heaters might come on. There was risk. Firing a thruster that is too cold can damage it. They did it anyway. And the reason they did it is the most American detail in this whole story. Deep Space Station 43 at Canberra. The dish that is the only way to command Voyager 2, and a critical asset for the network overall, was scheduled to go offline for months of upgrades. During that window, opportunities to command either spacecraft would be sharply limited, so the team was not responding to a crisis. They were clearing an item off a list before a maintenance shutdown. The way you replace a questionable part on a truck before a long haul because you know there will not be a shop for a while. In March of 2025, they sent the commands. The telemetry came back showing the heater temperatures climbing. The thrusters came back. Hardware that had been considered failed for 21 years. Working. Because somebody reopened a file. Every one of those saves depends on a resource the spacecraft is losing at a rate nobody can slow down. And it is measured in watts. The power source has no moving parts. And that is the first thing to understand about why it has lasted. Voyager 1 carries 3 radioisotope thermoelectric generators mounted on a boom extending away from the body. Held out there because they emit radiation the instruments would otherwise pick up. Each one contains 24 pressed spheres of plutonium-238 oxide. Plutonium-238 is not weapons material and it is not reactor fuel. It was chosen for one property. It decays by alpha emission with a half-life of about 87.7 years. And alpha particles stop within millimeters of solid material, which means all of that decay energy turns into heat right where it is produced. A fresh sphere glows red on its own, sitting on a bench, with nothing done to it. Surround the heat source with thermocouples, keep the far side cold by radiating into space, and the temperature difference across the junction produces a voltage. That is the entire mechanism. No turbine, no pump, no working fluid, no bearings. Nothing spins. There is nothing to wear out mechanically, which is why a device with no maintenance access has run continuously for 49 years. At launch, the 3 generators together produced about 470 watts. They have been declining ever since, for 2 separate reasons that stack. The first is the fuel. Every year, some fraction of the plutonium has decayed away, so there is less of it making heat. That decline follows the half-life, and it is completely predictable. The second is the thermocouples. They degrade. The materials in the junctions diffuse and change across decades of continuous operation at high temperature, and the conversion efficiency drops. That decline is harder to model, and it is why the actual power loss runs faster than fuel decay alone would predict. Together they cost the spacecraft roughly 4 watts a year. 4 watts does not sound like anything. Across 49 years, it is most of the power supply. Voyager 1 now runs on a fraction of what it launched with, and the number goes down every year whether anybody does anything about it or not. So the operation of this mission, for the last 3 decades, has been a series of decisions about what to turn off. They started with things that had no remaining use. 1980, after Saturn, several systems supporting the planetary encounter came off. 1990, the cameras, 6 weeks after the last mosaic came down. 2007, the plasma science instrument, which had degraded early and was drawing power for nothing. 2007 and 2008. The heaters for several instruments got switched off. This one is worth pausing on. The instruments stayed on. Their heaters did not. Every one of those instruments had been qualified to operate down to a specified temperature, and turning off the heaters dropped them well below it. They kept working. The cosmic ray subsystem had been tested down to about 58 degrees below 0 Fahrenheit. It spent years operating at temperatures approaching 100 below. Nobody at JPL will give you a confident explanation for that. The honest answer is that the parts were built with margins nobody ever characterized, by an industry that overbuilt as a matter of habit, and the equipment performs outside the envelope because nobody ever mapped where the envelope actually ended. Then, in the 2020s, the choices got hard, because there was nothing left that was not a science instrument. The team built a plan, not a crisis response, a schedule, worked out years ahead, listing which instrument comes off in which year, sequenced to get the most total science out of the remaining life of the mission. In February of 2025, the cosmic ray subsystem was turned off. That one had history. It was the instrument that first registered the cosmic ray increase at the heliopause, the counter that jumped 9% in August of 2012 and stayed up. It had been Ed Stone's instrument, in the sense that cosmic rays were what he built before he ran the mission. On the 17th of April, 2026, the low-energy charged particle instrument was shut down. Voyager 1 has 2 working science instruments left, the magnetometer and the plasma wave subsystem. The plasma wave instrument is the one from Chapter 16, the one listening to the hum. It is measuring interstellar plasma density continuously, which is the single most valuable measurement this spacecraft can still make. And it is on the short list precisely because of that. 2 instruments, out of 11 at launch. And the framing that matters. Said once, this is not a spacecraft failing. It is a spacecraft being managed down. Every shutdown buys running time for what is left. And the schedule was written by people who know exactly how many watts remain and exactly what each one costs. Our command has now been travelling for 23 hours. It reaches an antenna 12 feet across on a spacecraft weighing 1,600 pounds. The signal gets amplified, decoded, and executed by a computer with 8,000 words of memory that had part of itself relocated 2 years ago. The spacecraft carries out the instruction, then it answers, and for the next 23 hours, nobody on Earth knows what it said. 23 watts leave the spacecraft. The transmitter is a travelling wave tube amplifier, a technology that was already old when the mission launched, feeding a 12-foot dish made of graphite epoxy. The signal goes out the front of that dish as a cone, aimed at a planet that will not be where the spacecraft is aiming for another 23 hours. The navigation team accounts for that. They always have. For the first hour, the signal travels through interstellar plasma. This is the medium stellar ochre found humming in the quiet stretches of the archive. Denser here, thinner there. Structured at scales nobody could measure until a graduate student went looking between the loud events. The signal passes through it without noticing. Radio does not care about plasma at these densities. Around the 7th hour it crosses the heliopause and comes back inside the Sun's territory. There is no marker there. The counters that flipped in August of 2012 were reading particles, not radio waves. And the boundary that took a solar storm 13 months in transit and a dead instruments replacement to confirm does nothing at all to a signal passing the other way. It just crosses. By the 18th hour it has passed through the distance where, in February of 1990, a camera pointed backward and caught a planet in less than 1 pixel, sitting inside a streak of light bouncing around the inside of a lens assembly. Somewhere in the 22nd hour, it crosses Saturn's orbit. Down there, on the 12th of November, 1980, a spacecraft dove past a moon and got thrown 35 degrees north of everything, and gave up 2 planets for a photograph that came back orange. In the 23rd hour, Jupiter, where 1 frame of downlink got spent on a hunch and found a ring, and where a navigation engineer doing bookkeeping stretched the contrast on an image of Io and saw fire. Then the asteroid belt. Then Mars. Then, in the last few minutes of the trip, a blue planet with an atmosphere. The signal enters that atmosphere and bends very slightly. It comes down over the Mojave, spreads across a valley inside an army reservation, and a small piece of it lands on a steel dish 230 feet across. The power in that piece is around 1 billionth of 1 billionth of a watt. The amplifier is sitting in liquid helium, a few degrees above absolute zero, so the metal itself is quiet enough to hear it. The signal gets pulled up, locked, decoded, and put on a screen in Pasadena, where somebody on shift looks at it and confirms that the spacecraft did what it was told. Then they schedule the next pass. That is the whole job. It has been the whole job for a very long time now, and there is nothing in it that looks like the movies. A command goes out. 2 days later, you find out it worked. You write it down, and you do it again. Now, the ending. It comes in 3 parts, at 3 different times, and keeping them separate is the point. The science ends first. 2 instruments are running. The power supply falls by about 4 watts a year, and it does not stop falling. There will be a year when the remaining margin cannot support the magnetometer, and then a year when it cannot support the plasma wave receiver. And after that the spacecraft is still alive and still talking, and has nothing left to say about where it is. The team has that sequence planned. They have had it planned for years. It is on a spreadsheet in an office in Pasadena, and somebody updates it when the numbers move. The communication ends second. The transmitter needs power. So does the heater that keeps the hydrazine lines from freezing, and the computer that runs attitude control, and the thrusters that hold the antenna inside its quarter-degree cone. When there is not enough to keep all of that together, the pointing drifts, or the transmitter drops, and either way the signal stops arriving. The estimates put that somewhere in the 2030s, nobody at JPL will hand you a date. And the reason they will not is that this spacecraft has beaten every estimate anybody has made about it since about 1982. The journey does not end. Voyager 1 is moving away from the Sun at about 38,000 miles an hour, roughly 11 miles every second. There is no friction out there worth the name. The Sun's gravity is still pulling on it and still slowing it. But the spacecraft is well past escape velocity, and that deceleration flattens out toward nothing. It keeps essentially all of its current speed. Permanently. Nothing is going to stop it. Nothing is going to catch it. There is no scenario in which it comes back. Some year in the 2030s, a tracking pass comes up on the Deep Space Network calendar. It was scheduled months ahead. Because everything on that network is scheduled months ahead. And Voyager gets its allocation the same way the Mars Orbiters and Europa Clipper and everybody else does. A dish somewhere on this planet. California or Spain or Australia depending on the hour. Turns on its oil film bearing and comes to a stop, pointing at a spot in the sky where there is nothing to look at. The cryogenic system holds the amplifier a few degrees above absolute zero. The receiver locks to the frequency it has been locking to for over 50 years. There is nothing there. They will run the pass to completion, because that is the procedure. They will check the pointing prediction and the receiver configuration and the schedule, because that is also the procedure, and because the alternative to checking is guessing. They will try again on the next pass, and the one after that. At some point, somebody with the authority to do it will write a memo, and the mission will be declared complete. That is a bad afternoon in a building in Pasadena, out where the last signal came from. Nothing happens. The spacecraft holds the attitude it was last commanded to hold. Then the thrusters stop, and it begins a very slow tumble that nobody will ever observe. The generators keep making a little less heat every year, and eventually the difference across the thermocouples is not enough to push a current. The computers stop. The instruments are already cold. The antenna keeps pointing wherever it happened to be pointing when the last pulse fired, which will be roughly toward Earth, and it will drift off that mark over the following centuries because there is nothing left to correct it. And it keeps going at 11 miles a second on a heading it was handed by the gravity of Saturn on the 12th of November. 1980. Here is what happens after that. In numbers. Because numbers are the only honest way to say it. In about 300 years, Voyager 1 reaches the inner edge of the Oort cloud, the shell of icy bodies that supplies long-period comets. It will not detect them. There will be no instruments and no power, and by then no meaningful chance of an encounter anyway. Because the Oort cloud is enormous and nearly empty, and the odds of passing close to anything in it round to zero. In about 30,000 years, it passes beyond the outer edge of that cloud, as it is conventionally estimated. That is the point at which it will have left the solar system by essentially every definition anybody uses. And it is worth saying that the outer boundary of the Sun's gravitational reach is not a measured line. It is a best estimate with a lot of room in it, in roughly 40,000 years, around the year 40,272. It passes within about 1.7 light-years of a star called Gliese 445 in the constellation Camelopardalis. That is not a visit. It is not an encounter. It is the closest Voyager 1 will come to another star in a span of time longer than our species has had agriculture. And 1.7 light-years is about 10 trillion miles. After that, it joins the general population of the galaxy. It orbits the centre of the Milky Way the way the Sun does, the way every star does. On a circuit that takes something like 230 million years, the gold-plated copper record is bolted to the side of it the whole way. Interstellar space is not entirely empty. There is dust out there, moving fast relative to the spacecraft. And over long enough spans, the aluminum cover will be pitted and the exposed surfaces will erode. Estimates for how long the record stays readable run into the hundreds of millions of years, a number nobody can verify, which mostly tells you that gold on copper in vacuum is extraordinarily stable and micrometeoroids are extraordinarily rare. Sagan was clear about the odds of anyone finding it, and he never pretended otherwise. He said the record was for us. The uranium patch on the cover has lost a small fraction of 1% of itself since 1977. It will keep decaying at exactly the rate it has always decayed. And anything that ever finds it will be able to read the elapsed time off it the way you read a fuel gauge. So take stock of what is out there. 1,600 pounds of aluminum and titanium. A 12-foot dish. 16 nozzles smaller than your fist. Plugged with glass. 3 generators with no moving parts. A computer holding 8,000 words, with part of its program scattered into gaps by people working from a memory dump and a filing cabinet. 11 scientific instruments, 10 of them dark. A copper disc with 115 pictures of Earth on it, including a supermarket, a page of a book, and traffic in India. It was built by hand in a clean room in Pasadena by people in their 20s and 30s, most of whom are gone now. It was launched on a rocket that ran out of fuel with 3.5 seconds to spare. It was guaranteed for 5 years. It has been flying for 49. Nothing else humanity has ever made is close to it. Nothing on any drawing board is going to catch it. And it will still be the farthest machine we have built long after every person who worked on it wrote about it, or watched This Is Gone. It does not need us anymore. It stopped needing us the day the last watt ran out. And it kept going anyway, at the same speed, in the same direction, carrying the same disk, and bolted to the side of it, still running, still accurate, is a clock made out of uranium, still counting. Thanks for watching. Tell us in the comments which part of this machine stuck with you. The nozzle smaller than your fist, the chip that died and got worked around, or the clock on the side of it made out of uranium.